It is part 2 of section 14.6, maximizing the directional derivative. In the first part, we introduced the directional derivative, duf. U is a unit vector. It can be expressed as the dot product, gradient of f dot u. Using a well-known formula, we reach this term, where theta is the angle between gradient of f and u. Norm of u is 1, so we have this term. Cosine theta has values from -1 to 1, so we have this inequality. Of course, the inequality must be equal when cosine theta is 1. That means when theta is 0, then the directional derivative is the same as the norm of gradient of f. So we have here a theorem. F is a differential function of 2 or 3 variables, then maximum of the directional derivatives is the same as norm of the gradient of f. Of course, maximum is chosen over the direction. And now, as we saw from here, once u is chosen to have the same direction as gradient of f, then equality happens. Let's see this problem. F of xy is defined as x times e to the y. Find the rate of change of f at the point P, 1, 0, in the direction from P to Q minus 1 and 2. Okay, here, that's part A. We have to decide first the direction, the unit vector. The direction is given from P to Q. So terminal point is Q and beginning point is P. Q is -1 and 2, and P is 1 and 0. So we have here that is -2 and 2. Length is 2 times square root of 2. So divided by its length, we reach at the unit vector in the same direction as -1 over square root of 2 and 1 over square root of 2. Okay. To find the directional derivative, we need to get gradient of f. Right? Now, x derivative of the function is e to the y, and y derivative, x e to the y. Okay. Now, we have to evaluate the gradient at 1 and 0. X is 1, y equals 0. So 1, x is 1, y equals 0. So again 1. So gradient direction is 1, 1. So we have duf, that is gradient of f dot u. Okay. The gradient is 1, 1 direction, and u is -1 over square root of 2 and 1 over square root of 2. So if you get the dot product, then it must be 0. So for part A, 0 is the final answer. Now how about B? In what direction does f has the maximum rate of change? We already know that once we choose u, so that u has the same direction as gradient of f, then we can get the maximum directional derivative. Okay, so for example, if we choose u as the same direction, then the unit vector in the direction must be 1 over square root of 2 and 1 over square root of 2. Along with that u, now du of f, so that among all directional derivatives, this one will be the maximum value. Okay, so that is same as the gradient of f, which is 1 and 1 dot, and this one 1 over square root of 2 and 1 over square root of 2. So that is same as 2 over square root of 2, which is same as square root of 2. So when we choose the same direction as the gradient of f, then we have this maximum value. And also this theorem says that maximum of the directional derivatives is the norm of gradient of f. Okay, we'll try to use this formula. And gradient of f and norm, we have 1, 1. So that's square root of 1 squared plus again 1 squared. That is square root of 2. Either way, we have the same result. And we computed the result using that one and also using this one. But we have the same result. When we choose u to have the same direction as gradient of f, then the directional derivative is maximized. Okay? U is the unit vector in the gradient direction, so we can get this form. Then the directional derivative is written in this form in dot product, and u is replaced by the choice. Then these two dot product will make gradient of f norm squared and cancelled by 1 here, and we reach this one. This implies that the directional derivative is maximized in the gradient direction. So we have the one claim here. The gradient direction is the direction where the function changes fastest. More precisely increases fastest. The gradient direction is the direction where the function increases fastest. At this moment, I would say this one. Derivative is always increasing direction. You learned functions of one variable, I call fx. For example, the graph of this function is given in this way. Then here y prime, f prime, y prime at this point is increasing, so the y prime will be positive. And at this position, y prime is negative. Positive means the direction is here. Now negative means that direction. So this is always increasing direction. This is increasing direction. So derivative is always the increasing direction. And gradient for two or three variables, the gradient is the fastest increasing direction. Okay? Now we'll consider the gradient vector of level surfaces. let's begin with a level surface given in this way. Capital F, XYZ is K. As K varies, different level surface will be made. Now, for example, this figure is x squared plus y squared plus z squared with different k value is made. It's a sphere with different radius. Now, for this surface, let's consider a curve on the surface like that. This is curve. Then we can express the curve in this way. R of t is x of t, y of t, z of t. Now, we replace x, y, z by using the functions of t. Then we may consider this one as a function of t. So we may try to get derivative with respect to t, and using the chain rule, we have this one. First, we have to make f sub x, x derivative, and xt derivative, f sub y, and dy dt, and f sub z, dz, dt. By using the gradient notation, we can write in this way: gradient of f dot, that is now r, and r prime is x prime, y prime, z prime. So we have that. But this one is 0. After differentiation, right side must be 0. So 0 comes from this constant. Okay. This means that, okay, r prime is always tangential direction. Now curve is on the surface, so at this point, the r prime is on the surface. So if you make a tangent plane, then r prime will be on the tangent plane. And this is a vector on the tangent plane, and now gradient f, the dot product is 0. That means gradient f is the normal direction. Without that, it cannot be true. This is one single curve, but for any arbitrary curve, always this is true, which means now gradient f is a normal vector. Okay. Okay. And here, so we can summarize our derivation here. Given a level surface, the gradient vector is normal to the surface and pointing the fastest increasing direction. And earlier, we also got this information, conclusion. So gradient is always fastest increasing direction. And when we deal with level surface, then the gradient of f is normal to the surface. So that's the conclusion. It is similar to for level curves. Level curves are made in this way. And now, rather than x, y, z, we are using, for example, f of x, y equal k. Then in two-dimensional xy plane, the curves will be made along with different k. Now, if you consider gradient of f from the level surface, then now that is the normal direction to the curve, and that is gradient of f, and that direction is the fastest increasing direction. Okay. The exactly same way, this summary can be applied for level curves. So we can find the tangent plane and normal line. We already know that once level surface is given, then now gradient of capital F is a normal vector, so that the tangent plane can be obtained quite easily. And we choose an arbitrary point from the tangent plane. That is the point where we have to find the tangent plane. And at the point, gradient of F is normal. So that is exactly introduce an equation of the tangent plane. In detail, we can write this way. So dot product is 0. That is detail. Now, for normal line, and line R must be written this way. That is passing x0 and plus t gradient of F. That is direction. So normal line must be written in this way. Of course, R is here x, y, z. So by solving for t for 3 equations, we have that one. This is a symmetric form of the normal line. Okay. Find the equations of tangent plane and the normal line at point -1, 1, 2 to the ellipsoid. Okay, ellipsoid is given in this way. Now we can find the normal vector at the point to the surface by computing the gradient of F. Okay, that is x derivative is 2x, y derivative is 2y, and z derivative is z over 2. We have to evaluate this one at the point -1, 1, and 2. X is -1, then there is a -2. Y is 1, then it's 2. And z is 2, then that is 1. That is the normal direction. So here the tangent plane should have this form. And as if we try to use that one, then normal vector dot x minus x0. So that is now -2 and 2 and 1 dot that is x minus x0. That is -1, 1, 2. Okay. So we'll try to write down the detail. Okay, -2, first component, that is now here x minus x0 is -1, and plus 2, now y minus y0, which is 1, and finally plus 1, that one, 1 times z minus z0, which is -2. That is 0. If you want, you can simplify this one to get the final answer. Now, how about normal line? Normal line is now R is same as here the point x0 plus t and gradient of F. Okay, that is in detail. X0 is -1, 1 and 2, and times t, and gradient of f is minus 2, 2, and 1. Right? Of course, r is the same as xyz. Okay. So that is the vector form. If you want to get the symmetric form, then you have to solve for t. So move this one to the other side and divide by that quantity. Then you can get, so we focus on only this portion. And from first equation, t is the same as, now, okay, look at here, x plus 1 divided by minus 2. And from second one, t is, now move this one, so y minus 1 divided by 2. From the last one, and z, okay, minus 2 divided by 1. So that is the symmetric equation for the normal line. This is a figure at the point. This is the tangent plane. That is the normal line. By using Maple, I made this figure. Okay. Okay, that's the end of section. Thank you.